In this class, we will discuss um, measurement in a quantum system or a quantum measurement. Let us start with the sequential, one of the sequential Stern-Gerlach experiments that we had discussed in the first 2-3 classes. Um, consider a beam. This is in the initial state with the spins oriented in random directions. Then we use a Stern-Gerlach apparatus that measures spin in the z direction. And what we see is that nearly 50% of the particles are having spin component plus h cross by 2, and the other 50% particles are having spin component minus h cross by 2. So those with spin component plus h cross by 2 are deflected upward, and the other half of the beam are deflected downward. And this state with the spin component Sz equal to plus h cross by 2 is denoted by this ket Sz plus, and this is Sz minus. Okay. So what do we deduce from this experiment? One thing is that when the initial state of the system is a general state for the physical quantity being measured. What is the physical quantity being measured here? Sz, z component of the speed. So for this physical quantity, if this initial state is a general state, then after the measurement, the system changes from the general state to one of the eigenstates of this operator corresponding to this physical quantity. Okay, the physical quantity is this, and we have an operator corresponding to this physical quantity. These are the eigenstates of the operator as set. So after the measurement, the system changes from the general state to one of the eigenstates, and the result of each individual measurement is one of the eigenvalues of this operator. Okay, this plus h cross by 2 and minus h cross by 2 are eigenvalues of this operator. So if we consider this measurement one particle at a time, okay, each particle will be deflected either upward or downward. That means those with the deflection upward are having the eigenvalue Sz equal to plus h cross by 2. The particle that is deflected downward is having the eigenvalue Sz equal to minus h cross by 2. So the result of each individual measurement is either plus h cross by 2 or minus h cross by 2. One of the eigenvalues of this operator. Okay. It's a spin-half system, so this operator has only two eigenstates and correspondingly two eigenvalues. Okay. So this is what we have obtained. So let us try to generalize this idea. Okay. If the system is in a general state, let's say ket alpha. Okay, this is the initial state. So if the system is in an initial state, then as a result, the initial state is a general state. Then if we make a measurement, okay, what is the final state? Final state is an eigenvalue ket A prime, and the measured result is the final state is an eigenstate ket A prime, and the measured value is the eigenvalue A prime, and this eigenstate is corresponding to this eigenvalue. You can notice that this eigenstate is labeled after this eigenvalue. Okay, so the result of the measurement is this eigenvalue, and the final state is ket A prime. Okay, the system undergoes a change from the initial state, general state ket alpha to the eigenstate A prime. And this change is often called collapse of the initial state to the eigenstate, or a quantum jump. Okay, so that we can say that the state undergoes a collapse from the general state to an eigenstate, or a quantum jump from the general state to the eigenstate. So this is let us say this is our trial 1. Okay, then let us say this is trial 2. In trial 2, again we start from the same initial state. Okay, then we do another measurement. We do a measurement. This time the result of the measurement is, let us say, the eigenvalue A double prime. Then the final state is the eigenket or eigenstate corresponding to this eigenvalue. Okay, so now it collapses from the general state to another eigenstate. Okay, so the result of each individual measurement is one of the eigenvalues of this operator that we are measuring. Suppose we are measuring the physical quantity, let us say A. Okay. The one of the eigenvalues of the operator A, and the final state is one of the eigenstates. Okay, the system collapses from the initial state to the eigenstate corresponding to this eigenvalue. Okay. Now here there is a problem. When we make a measurement, a quantum measurement, we should always ensure that the system starts from the same initial state. That means in order to repeat this measurement, we should always we should be assured that we are starting from the same initial state. Okay, how do we ensure this? If we have only a single system to make measurement, then we know that as a result of the measurement, the state will change. Then how do you repeat the measurement? It's not possible to bring it back exactly to the initial state. Maybe theoretically it is possible, but experimentally it is cumbersome to bring it back exactly to the initial state and then restart again. So a practical way to overcome this problem is, what we do is we make identically prepared collection of systems in the same initial state. We make identically prepared systems in the same initial state or in the same state. Okay, and this collection of identically prepared systems in the same state is called a pure ensemble. Ensemble means collection. So to make a measurement, we always do this. We ensure an identically prepared systems, a collection of identically prepared systems, all in the same initial state. Then we can do trial 1, then take the next system from the ensemble, do trial 2, etc. We can do as many trials as possible, because we are assured that all the systems in the ensemble are in the same initial state. Now how do we practically do this? Let us consider this Stern-like experiment again. One of the sequential experiments that we had discussed in the initial classes is, see, we start with the initial state where spins are randomly oriented. Then we make this Z spin measurement in the Z direction. So we have nearly half the particles are in upspin state, okay, with Sz equal to plus h cross by 2. The other half are in the downspin state with Sz equal to minus h cross by 2. And we stop this beam here. The Sz minus beam we have stopped here, and this beam we use for further measurements. Okay. So look at here. Now all these particles, let us say some 1000 particles are here. All these 1000 particles are in the same state, Sz equal to plus h cross by 2. ket SZ plus. Okay, this is an example of a pure ensemble. Okay, so this is an example of pure ensemble, and this type of preparing a pure ensemble, this type of measurement is called a selective measurement. Selective measurement. Okay, out of particles oriented in where spins are oriented in random directions, we select 50% of particles with the spin exactly oriented with plus h cross by 2, SZ equal to plus h cross by 2. So it's a selective measurement, or another name is filtration. The Stern-Gerlach apparatus, first Stern-Gerlach apparatus here acts as sort of a filter. It filters half the particles with SZ equal to plus h cross by 2. So by selective measurement or filtration, we can construct a pure ensemble. This is an example of pure ensemble. Okay. And so we understand, we have seen this case of an initial state undergoing collapse into one of the eigenstates as a result of measurement. Now suppose when we start a measurement, suppose the initial state is an eigenstate itself, an eigenstate of the operator. Okay, then what happens? We also look at another sequential experiment we considered. For suppose we prepare a pure ensemble like this, and we again repeat this SZ measurement, spin component measurement along the Z direction. What is the result? The input is all the 1000 particles are in the SZ plus state. Then if you again measure SZ component, SZ spin, what you get is output, all these particles are in the same state, SZ plus. Okay, and here no particles with SZ minus. So what does it mean? See, SZ plus is an eigenket or eigenstate of the physical quantity being measured, which is the Z component of the spin. Okay, so the initial state here in the second Stern-Gerlach measurement, the initial state is an eigenstate. It itself is an eigenstate. In this case, initial state is a general state. It's not an eigenstate of SZ. Okay, that's why it undergoes a collapse into 50% particles are undergoing quantum jump into SZ plus, the other 50% undergoing quantum jump into SZ minus. But here, in the second Stern-Gerlach measurement, initial state is an eigenstate of SZ and it remains in the same eigenstate. In general, we can say if the initial state is ket A prime, one of the eigenstate of the physical quantity being measured, then as a result of a measurement, this is the final state. There is no change. It remains in the same eigenstate. And what is the result of measurement? Surely it is always the eigenvalue A prime. Okay. If you repeat this measurement again, you will get the same eigenstate with the same eigenvalue. Now we know that the general state, let us say ket alpha, can be expressed as a linear combination of base kets. Okay. Now, if our physical quantity is A, and again, let's say A is the operator corresponding to that physical quantity, and suppose these are the eigenkets of this operator A prime, ket 1, ket 2, ket 3 up to ket n, like that. Then we know these are Hermitian operators. Eigenkets of a Hermitian operator form a complete set. So the set of eigenkets of a Hermitian operator can be chosen as one basis of the vector space. Okay, that means a general ket can be expressed as a linear combination of the eigenkets of the Hermitian operator corresponding to the physical quantity being measured. So let us say we are trying to measure a physical quantity A when the state of the system is in alpha, as here. Then what we do is, let's assume that this general ket is expressed as a linear combination of the base kets, which are the eigenkets of this particular physical quantity or this particular operator. Let's say, so we can write it as summation over A prime, C A prime, ket A prime. Ket A prime are the eigenkets of the operator that is being measured in this state. Ca prime are the expansion coefficients. And how do we calculate this Ca prime? Ca prime is inner product between A prime and alpha. So ket A prime and ket alpha. In other words, it is a component of ket alpha along the direction of ket A prime. So we can substitute that here. So this is summation over A prime. I can substitute it here, and usually the ket vector is expressed first. Then if you write it, okay. We can also understand this expression as summation over A prime, ket A prime, bra vector A prime is identity. It's the completeness condition of the base kets. So it's just like identity times alpha, and the identity is expressed like this, completeness condition. That's another way of getting this expression. Okay. Now if we expand this, it will be like this. Instead of this, let me use CA again. So it is something like this, C1. Instead of A prime, let me use subscript. So it is something like C1 ket A1 plus C2 ket A2 plus C3 ket A3 plus C4 ket A4, etc. Expansion is something like this. So in trial 1, what happens from the general ket, let us say it collapses to, let us say, this base ket, this eigenket, ket A2. What is the result of measurement? A2. In trial 2, it collapses from this to, let us say, A4, ket A4. What is the result of measurement? The eigenvalue A4. So it goes like that. Okay, this is the way it collapses. So the point is that this general ket contains some component of each eigenket of the physical quantity being measured. So in each measurement, what happens is the state collapses from the general ket to one of the eigenkets, and the result of measurement is the corresponding eigenvalue. In the next trial, it collapses to some other eigenket, and the result of measurement is the corresponding eigenvalue A4. It goes like that. We cannot predict to which eigenket it will collapse. In other words, in a particular trial, we cannot predict which eigenvalue we are going to get. It can be A1, it can be A4, it can be A7, it goes like that. So the collapse is completely arbitrary, random. It's a random process. We cannot predict to which eigenket the system is going to collapse, or what is the result of each individual measurement, which eigenvalue we are going to get. We cannot predict. But we can predict the probability of getting a particular eigenvalue as the result of measurement. In other words, we can predict what is the probability of the system being collapsed from a general ket to one particular eigenket. What is this probability? Probability of getting the eigenvalue A prime as the result of an individual measurement. What is this probability? This probability is this quantity, the inner product between A prime and ket alpha. What is ket alpha? It is our initial state where the measurement is made. Let us assume that ket alpha is a normalized state. Okay, so and the result of an individual measurement, I will add it here, in the normalized state ket alpha. Okay, so we are making a measurement in the normalized initial state ket alpha. What is the probability of getting A prime as the result of an individual measurement? So we have to take the inner product between A prime and alpha, and its model, it's in general a complex number, it's square. This is the probability. Okay, probability of getting A prime, the eigenvalue A prime as the result of an individual measurement in the initial normalized state ket alpha is A prime, inner product between A prime and alpha whole square. We know that this okay, so this can be generalized like this, or I can make a general statement about it like this. What happens, so if A prime, if you get A prime as the result of an individual measurement, then what type of collapse takes place? From the initial state ket alpha, the system collapses to the eigenstate ket A prime. Okay, the eigenstate corresponding to this eigenvalue. So it means that if this is the initial state, then this is the final state. Ket A prime is the final state. So this inner product is between the final state, it is in the bra vector side, and the ket vector side you have the initial state, modulus square. This is how we calculate the probability of getting a particular eigenvalue as the result of a measurement. In other words, probability of getting a particular ket as the result of a measurement. So what we have to do, we have to take the inner product between that particular final state and the initial state and square of that. That is the probability. Okay. And we know that this inner product between A prime and alpha is the component of alpha along the direction A prime. This is the expansion coefficient, okay, corresponding to the eigenket A prime. So this is actually modulus of C A prime square. So the probability of getting a particular eigenvalue is the square of the corresponding expansion coefficient in the expansion of ket alpha in terms of the eigenkets. Because of this reason, this C A prime are also called probability amplitudes. Probability amplitudes. The expansion coefficients in the expansion of a general ket in terms of the eigenkets. These expansion coefficients are also called probability amplitudes. The reason is the square of this expansion coefficients give you the probability. Okay. Okay. Now let us see if this makes any sense. Let us verify whether this this expression satisfies the properties of a probability. Two important properties of any definition of probabilities. One is that it should be positive always, okay, and this, since it's a square of a complex number, modulus square of a complex number, we can be assured that this inner product between A prime alpha square is always greater than or equal to 0. Okay, so that is always assured. This if it is probability, it should be greater than or equal to 0. It can never be negative, and since it is a square, it will always be greater than or equal to 0. That is one point. And second aspect is, if we take the summation of probabilities over all possible states, then we should get 1. Okay. So this is the probability of getting A prime as a result of a measurement. Similarly, A double prime, A triple prime you can calculate, and you can take sum over all eigenkets. Then that should be 1. Let us see if it happens. So what is this summation over A prime alpha square? The sum of these probabilities over all possible eigenkets. Okay, so something like A1 alpha square, that's the probability of getting eigenvalue A1 as the result of a measurement. A2 alpha square is the probability of getting A2 as the result of a measurement, and so on. So if we consider all eigenvalues, that means all eigenkets, then what is the total probability? Let us see if it is 1. This is equal to summation over A prime, and we know that this is expansion coefficient, so it is modulus C A prime square. In one of the previous classes, we have shown that if ket alpha is normalized, what is a normalization condition? Bra vector alpha, ket alpha square. No, this is equal to 1, right? If this is normalized, this is equal to 1. Okay, now we can show that this is equal to summation over A prime mod C A prime square is equal to 1. So if we start with a normalized ket, okay, you expand this ket vector and bra vector over eigenkets, and then you can base case. Okay, then you can show this. Okay, because using the normalization condition of base case, you can show that this can be expressed like this. Okay, this we have discussed in one of the previous classes. So here we have assumed that the initial state ket is a normalized state ket. That means bra vector alpha ket alpha is equal to 1. That implies that summation over CA prime square is equal to 1. So that means this quantity is 1. But this quantity is nothing but the sum over all states of probabilities. So this satisfies this property of probability. Total probability is 1. So this also shows that if a state is normalized, it implies that the total probability is 1. Okay. So if this is the definition of a probability, it satisfies two basic requirements of probability. One is that it should be non-zero, and second is that total probability is 1. Okay. Let us further see it makes any physical sense. Okay. So let us consider this definition of probability in two extreme cases. Okay. So as a first case, I will take let ket alpha is equal to ket A prime. Okay. Suppose the initial state is an eigenket. Physically, we know what it means. If the initial state is an eigenket, we have just seen it in one of the previous diagrams of sequential Stern-Gerlach measurements. If the initial state is an eigenket of S set, okay, let us say it is S set plus, then what is the result of further measuring S set? We get all the particles in the same S set plus state. Okay, so if the initial state is an eigenstate of an operator being measured, of a physical quantity being measured, the system remains in the same state. That is why it is called eigenstate. That is why this state is a characteristic state or a special state or a unique state for that operator, which we call eigenstate. So physically what happens if the initial state is an eigenstate, the system should remain in the same eigenstate, and suppose it is ket A prime, then the result of the measurement should be the eigenvalue A prime, 100% sure. Okay. So let us see if we get that from this expression of probability. So if initial state is eigenstate, what is the probability the probability of getting A prime? Probability of getting A prime. Physically, what should be the probability of getting A prime? We know that surely you will get A prime because initial state is ket A prime. Okay, then if you measure the physical quantity, you should surely get A prime. There is no probability, 100% sure. The probability is 100%, we can say. If the initial state is in S set equal to plus h cross by 2, if you further measure S set, then all the particles will be surely in S set equal to plus h cross by 2. Okay, like that. So what is the probability? Mathematically, do we get this? Let us see. Probability of getting A prime according to this expression is, so the final state is A prime. Okay, we have to take the inner product between final state and initial state. So on the bra vector side, you have the final state, which is A prime. On the ket vector side, you have the initial state. But what is the initial state? It's again A prime, the same eigenket. So it is like this. This is the probability. But what is A prime inner product with A prime? A prime is already eigenket. It's normalized. Okay. So this is 1. So the square is also 1. Probability is 1. That means 100. In terms of percentage, it is 100%. So what is the probability of getting A prime? It's equal to 1 means surely you will get A prime as the result of measurement. We know that physically it should happen, and from this definition of probability also we get the same result. So it is 100% sure. It's a double statement. 100% means sure. Okay, 100% or sure, we can say. Consider the next extreme. So this is in a sense, this represents the normalization of eigenkets. Okay, this extreme case. Consider another extreme case. Again, let ket alpha is equal to A prime. We start with the one of the eigenkets. This time I will calculate what is the probability of getting a double prime? I mean, an eigenvalue corresponding to another, a different eigenket. What is the probability? Okay, let us calculate according to this equation. Before calculating, what should be the physical situation here? The initial state, let's go back to our Stern-Gerlach sequential measurement. The initial state is SZ plus state. Okay, that means all the, let's say, 1000 particles are in the state SZ equal to plus h cross by 2. You make a further measurement of SZ. What do you get? All the particles, all the 1000 particles are remaining in the same eigenket, SZ plus. There are no particles with SZ equal to minus h cross by 2. So if the input state is SZ plus, then the output state is necessarily, surely SZ plus. Okay. There will not be any other eigenvalue corresponding to the other eigenket, SZ minus. We won't get SZ equal to minus h cross by 2 if the input is SZ equal to SZ plus state. Okay, that is, SZ plus state and SZ minus state are mutually exclusive. If the input is SZ plus, you won't get SZ minus. If the input is SZ minus, you won't get SZ plus. They are mutually exclusive. Mathematically, we say they are mutually orthogonal. Okay, so if the input state is, let us say, get A prime, and what is the probability of getting A double prime as the result of the measurement? Where A double prime is the eigenvalue corresponding to a different eigenket. What is the probability? It should be 0. We will never get. They are mutually, because ket A prime, the initial state, and ket A double prime are mutually exclusive. Okay. So let us see, mathematically we will get that from this definition of probability. So what is the final state we are trying to see? If this is the, we want to calculate the probability of getting A double prime. In other words, we want to calculate the probability of getting ket A double prime as the final state. We are asking the question, is it possible that from this general state, a ket A prime, a collapse into ket A double prime is possible? That's what we are asking. What is the probability? So the final state that we are postulating, hypothesizing, is ket A double prime. So it should appear in the bra vector side, the final state. And what is the initial state? This one, ket A prime. So what is the probability? This is the probability. But what is this? This is the inner product between two different eigenkets. We know that eigenkets of a Hermitian operator are mutually orthogonal. So this inner product should be 0. Okay, if this is 0, square is also 0. So no chance. Probability is 0. So these are two extreme cases. In one case, we ask the question, if the initial state is in a particular eigenket, what is the probability of getting the same eigenvalue or the same eigenvalue as the result of a measurement? 100%. That's what we get. The system will remain the same eigenket. Okay, no doubt about that. 100%. 1. If the initial state is a particular eigenket, what is the probability of getting a different eigenvalue corresponding to a different eigenstate as a result of measurement? No chance. Okay. So in the first case, extreme case, we have considered the normalization of the eigenkets. In the second case, we have considered the orthogonality of eigenkets. So in these two extreme cases, this definition of probability works. So let us accept it as we have checked it in various ways. It satisfies the basic properties of probability, non-zero and total probability is 1. It also satisfies, it also works good in the physical situation. We have considered these, we have considered. So let us take it as the probability of getting a particular eigenvalue as the result of measurement. So as I have stated earlier, we cannot predict which eigenvalue we are going to get as a result of a particular individual measurement. We cannot say whether it is A1 or A2 or A3 or A4. We cannot say. But we can predict the probability of getting A1. What is the probability of getting A2? What is the probability of getting A3? Starting from a particular initial state, we can always predict, we can always calculate what is the probability of getting a particular eigenvalue as the result of measurement. This is how. Okay, inner product between the final state, whatever final state we want, corresponding to the particular eigenvalue, and the initial state, and take the square. That is the probability. This is a fundamental postulate in quantum mechanics. It's a postulate. And where do you get this from? by observing different experimental results, as in the case of sequential Stern-Gerlach measurements, as in the case of measurements of light polarization. Okay, by observing such phenomena, we introduce this. It's a fundamental postulate. Next, we consider this quantity expectation value. Okay, so expectation value means it means average value. Average value of a large number of measurements. Okay, so we make a large number of measurements of a physical quantity, take the average value, that's called expectation value. So how do we define the expectation value of a physical quantity? So suppose we measure a physical quantity in a state ket alpha, then the expectation value of the operator corresponding to the physical quantity, we use this notation symbol A. Suppose we are measuring the physical quantity A, then suppose A also represents the operator corresponding to the physical quantity, then we put A in angular brackets. This is called this is the symbol for the expectation value. And sometimes if you always measure the expectation value when the system is in a particular state, let's say ket alpha. Then we also put a suffix here, alpha, to show that, to specify that expectation value is being measured or calculated with respect to the state alpha, the initial state alpha of the system. And okay, how do we define it? It is defined as bra vector alpha operator A ket vector alpha. This is the definition of the expectation value of an operator or of a physical quantity. Now this looks very unfamiliar, or this doesn't look like an average of a large number of measurements. Okay, what we have stated just before is that the result of each individual measurement is one of the eigenvalues. Okay, then you make one trial, you get one eigenvalue, you make second trial, you get another eigenvalue. Okay, in first trial you get A1, in second trial you get A7, in third trial you get A5, like that it goes. Maybe you make 100 trials, you get different eigenvalues. Okay, in some of the measurements you get the same eigenvalue, and it goes like that. Then how do you can calculate the average of a large number of measurements, but this equation doesn't look like that. How do you connect, how do you show that this equation gives you the average value in terms of the eigenvalues? Okay, let us see how it comes. So let's try to verify whether this definition of expectation value is makes any sense, or it's actually the average of a large number of measurements. So we are going to verify that. So let's say verification. So I will show this in two different ways. First, let us go to take the longer route, and then finally I will show what's the easiest way to get that result. Okay. So what we do is we know that this ket alpha can be expanded in terms of base kets. Which base kets we are choosing? If we want to measure this operator A, physical quantity A, then we choose the eigenkets of this operator A as the base kets. Okay, so and we expand this state general ket alpha in terms of the eigenkets of the physical quantity being measured or the operator being measured. So how do you expand it? So summation over A prime, ket A prime alpha, right? This summation over A prime, ket A prime, vector A prime is the identity. These eigenkets form a complete state, so this identity equal to 1 is the, this summation is equal to 1, identity is the completeness condition. Okay, we use that condition here. So ket alpha we can substitute this, and what about bra vector alpha? So if you invert this, what is bra vector alpha? So this gives bra vector alpha equals summation over a prime. Okay, you have to invert, take the adjoint of this one. So this will become, this ket will become bra vector, and this is a scalar. Okay, so we have to take the complex conjugate of the scalar. So we get a prime alpha star. This is the adjoint. So let us substitute this here and this here. Okay, but when you substitute, we have to use the basic rule is that in an inner product, when you substitute an index, when you use an index on one side and another side, you have to use different indices. Okay, so let us use a prime for the ket vector side. Okay, let us substitute this for the ket vector side. For the bra vector side, I am using a different dummy index. It's a dummy index, so let me use a double prime. Okay, we are summing over all eigenkets. So whether we use a prime or a double prime or I or j or m or l, it doesn't matter. Okay, so we can use a different notation here. So what is this expectation value? Again, we have assumed that this ket alpha is normalized. Okay, I will write down the equation for unnormalized case later. Okay, so this ket alpha expectation value of A is equal to, so here I am substituting this summation over a double prime. I will write this first, the scalar. So a double prime alpha star, and then bra vector a double prime. Okay, so this is the this one, bra vector alpha, and then there is operator A. Okay, and the summation over a prime, this. Okay, the summation over a prime, let me write here, and then we have this part. Okay, so get a prime alpha. Now look at here. This ket A prime is the eigenket of operator A. Then when A acts on A prime, you get A prime times A prime. So this looks like A prime eigenvalue A prime times ket A prime. This eigenvalue A prime is real. It's a Hermitian operator. Eigenvalues are real. I can take it outside the inner product. So we get A prime, then bra vector A double prime, ket A prime. This part. Now these two are two different eigenkets. They are orthogonal to each other. So we can write it as delta A prime A double prime. A Kronecker delta. If A prime is equal to A double prime, it's 1. If A prime is not equal to A double prime, it is 0. Okay, orthonormality condition. So let's substitute this in our summation. So we have sum over A prime, sum over A double prime, A double prime alpha star, then write here, or let us write here A prime delta A prime A double prime, then we have this part A prime alpha. So you have a Kronecker delta within a summation. You have two summations. Take any one. Let's take this summation, summation over A double prime. You have a Kronecker delta delta A prime A double prime. It means that in this summation only one term will remain. Only one term will be non-zero. Which term? When A double prime is equal to A prime, then this Kronecker delta is 1. For all other terms, A double prime is not equal to A prime. Okay, so for all these terms, Kronecker delta will be 0. So all the other terms in this summation will go. Only one term will remain. Which term? Corresponding to A double prime equal to A prime. Okay, so you have to put A prime here instead of A double prime. You have to put A prime here also for A double prime. So what you get is sum over A prime. This summation will be there, but this summation is going. For which summation is going, you can choose either this or this. I am choosing this, that's all. So this, in this expression, you have to put A double prime equal to A prime. So you have A prime alpha star, then you have A prime, and in this Kronecker delta, A double prime is equal to A prime. So delta A prime, that is 1. That's 1. Then you have this. Okay. Yeah. Then what is it? Summation over A prime A prime. This is A prime alpha star, this is A prime alpha, which means you have A prime alpha mod square. Okay. Now earlier we have said that this A prime alpha mod square is the probability of getting A prime, eigenvalue A prime as the result of an individual measurement. What is this eigenvalue A prime? So what is this summation? Let me write it here. Maybe I will write it here. This is equal to what finally what you have got. What you have got is summation over eigenkets. Okay, I will write in here summation over eigenket. Then what is this A prime? This A prime is result of each individual measurement, right? We know that the result of each individual measurement is one of the eigenvalues. So this is one eigenvalue. It's the result of each individual measurement. What is this? This is the probability of getting one particular eigenvalue as the result of a measurement. So this is probability of getting that value, that eigenvalue. Okay, so result of each individual measurement into probability of getting that value, plus we are summing over all eigenkets. So plus you take the next value, next result of individual measurement and probability of getting that value. So each eigenvalue times probability of getting that value, plus eigenvalue times probability of getting that value. Something like A1, P1, A2, P2, A3, P3, etc. That is nothing but the average of all these measurements. Okay, so this is nothing but average value. Okay, so this is like a weighted average of eigenvalues or the average of a large number of measurements. So we have started from this definition of expectation value, and we have got this standard in probability theory. This is a standard expression for the average of a quantity. Okay, take each individual measurement, multiply with the probability of that measurement, take the next one, multiply with the probability, and sum over each value into probability of that value. That is average value. Okay, that's how we calculate average value of a collection of any data set. So what we have done is we have verified that this definition of expectation value exactly corresponds. This definition of expectation value exactly corresponds to the average value of a large number of measurements. So we have done this verification in one way. Now let us look at an easier way of getting the same result. Now in this case, what we do is, in the earlier method, what we have done is we have expanded this ket alpha and bra vector alpha in terms of the eigenkets of operator A. Now an easier method is take this operator A and express it in terms of its own eigenkets. Okay, this we have done in the previous class. How do we express the operator A in its own eigenkets? Summation over A prime, eigenvalue A prime, and this projection operator, ket A prime, bra vector A prime. This is the expression of operator A in its own eigenkets. In order to see how we get this, you refer to the previous class. So what I am going to do is, let us substitute this value here. Okay, then let us see. So the expectation value of A you can write as, from here, bra vector alpha. Instead of operator A, I am going to substitute this. So summation over A prime, eigenvalue A prime, ket A prime, bra vector A prime. This is our operator A. Okay, and then you have ket alpha. Suppose you write the summation first. So summation A prime. Then what is remaining? There is a number here. A prime is the eigenvalue. Let me write it here. Then what is remaining? You have bra vector alpha. Then you have ket A prime. Then you have bra vector A prime. You have ket alpha. Look at this. What is this? Summation over A prime, A prime. What is this? This is A prime alpha. This is alpha A prime, which if you interchange the order, you have A prime alpha star. So in other words, modulus A prime alpha square. This is the result. Okay. So sum over eigenvalue times probability of getting that particular eigenvalue, which is the average of a large number of measurements. So this is easier. Instead of expressing this ket alpha and bra vector alpha in terms of base kets, in terms of the eigenkets of A, just directly express operator A itself in terms of its own eigenkets. Then you will easily reach the same result. So this result shows that expectation value is nothing but the weighted average of eigenvalues. Okay. So it should be very clear that eigenvalue and expectation value are two different things. Okay. Eigenvalue is the result of each individual measurement. Expectation value is the weighted average of a large number of measurements. We have seen the probability of getting a particular eigenvalue as the result of an individual measurement, and also the expectation value of a large number of measurements. In both cases, we have assumed that the initial state, this ket alpha, is a normalized state. Now, what if it is an unnormalized state? Okay, in principle, we can normalize all the states, but what if it is an unnormalized state? Then, how do you write the expression for this probability and the expectation value? Now, if alpha is unnormalized, okay, if ket alpha is unnormalized, okay, probability of getting A prime as the result of an individual measurement is, we can write like this: A prime alpha square divided by this. You have to divide with the norm of the ket alpha. Okay, and what is the expectation value? Okay, expectation value of A is, again you have to divide with the norm of alpha. Okay. So here this quantity, if you express in terms of the expansion coefficients, this will be like this. Numerator is same. This will be sum over A prime okay, this quantity will be like this here also. Okay, so this will be the probability, and this quantity you can similarly, if you start with this quantity, you can show that this will lead to summation over A prime times the probability, where the probability will be this. That means you will get this A prime alpha square divided by sum over A prime okay. So this is the difference. This will be the probability. And the basic result is the same. Sum over eigenkets, eigenvalue times probability of getting that eigenvalue. Probability of getting that eigenvalue is this. Okay, so you have to divide with the norm. That's it. So this or this is the norm of the is initial state ket. So this is the difference if we use an unnormalized initial state. If it is normalized, then only the numerator part we need to consider. In order to understand the difference between eigenvalues and expectation value, let's consider again Stern-Gerlach measurement. Let us say we are measuring this S set, Z component of the spin. Then The result of individual measurements is we know plus h cross by 2 and minus h cross by 2. Either plus h cross by 2 or minus h cross by 2, and these are the eigenvalues of the operator Sh. These are the result of individual measurements. If you make one measurement, you will get either upspin or downspin, either plus h cross by 2 or minus h cross by 2. These are the eigenvalues. Now, what is the expectation value of Sh? The expectation value of Sh, always remember that expectation value is measured with reference to a particular state. So, with reference to which state you are measuring the expectation value, that by that choice of the state, the expectation value can be different. Okay. So, in general, the expectation value of Sh in this particular case can be any real number between plus h cross by 2 and minus h cross by 2. Okay, let us consider some examples. Suppose ket alpha is equal to this state, Sh plus. Remember that this is one of the eigenkets of Sh operator. So, if the initial state is this, then all the particles will be in the same state after the measurement of Sh. If you are measuring Sh again, then suppose there are 1000 incoming particles all in this state. If you are measuring Sh again, all the particles will continue to remain the same eigenkets. We have seen this experiment. Consider this experiment. If all the, so that means if you make 1000 measurements, all these 1000 particles will be in the state Sh equal to plus h cross by 2. So, what is the result of these 1000 measurements plus h cross by 2? Then what is the average value? So, this gives the average value is plus h cross by 2. Because all the individual measurements yield plus h cross by 2. Average value is also plus h cross by 2. If the initial state is Sh minus, surely the average value will be, all the particles will be in the state minus h cross by 2 after measurement. So, the average value is surely minus h cross by 2. Okay. Then you consider the initial state, let us say Sx plus. Then this experiment we have discussed in the earlier, the first 3 classes. If this is the initial state, then 50% of the particles will be in Sh plus state, and the next 50% particles will be in Sh minus state. Okay, so that means nearly half the particles will be having the spin z component of the spin plus h cross by 2. The other half will be having spin component, nearly half will be having spin component Sh equal to minus h cross by 2. So, if we take the average value, what will be the result? Average value will be 0. Okay, if 50% particles are having plus h cross by 2 and 50% particles are having minus h cross by 2, average value is 0. Consider another case. Suppose the initial state is something like this, root 3 by 2 Sh plus say 1 by 2 Sh minus. Suppose the initial state is like that. Then how do we calculate Sh, the average value? Let us use the result, that the standard result, that is summation over a prime times probability of getting a prime, right? If we use that result, what is this probability actually? It is the square of the expansion coefficients, right? So we have got these expansion coefficients. Okay. These are nothing but what is this quantity, inner product between a prime and alpha whole square, that is the square of the expectation values. So we have square of the expansion coefficients. So we have this expansion coefficients here, we need to take only the square. So let us calculate this. So this is equal to, what is the first eigenvalue? This one, plus h cross by 2. So plus h cross by 2 into, what is the probability? Square of this expansion coefficient, which is 3 by 4. Okay. Next expect eigenvalue is minus h cross by 2. We have only 2 eigenvalues here. So this summation contains only 2 terms. minus h cross by 2. What is the probability? Square of this expansion coefficient, 1 by 4. So we have x cross by 2 times 3 by 4 minus 1 by 4, which is 3 by 4 minus 1 by 4 is 2 by 4, 1 by 2. So we have h cross by 4, that is 0.25 h cross. That is the average value if the initial state is this. So depending upon the initial state where you make the measurement, then the average value can be any real number between plus h cross by 2 and minus h cross by 2. Here it is 0, here it is 0.25 h cross. So if you tweak this initial state, if you tune this initial state, then you will get any real number between plus h cross by 2 and minus h cross by 2. These two are the extreme cases where the initial state is one of the eigengates, okay, of the operator. So this is the difference between eigenvalues and expectation value. Okay, in this case there are only two eigenvalues, but the expectation value can be between any real number between this and this. Okay, yeah, that depends upon the state in which we are making the measurement.